Good morning. Just need to do a video for concrete. This is not for first year person. This is for more like third year person. So guys, don't mind if you are not third year. So this is based on this book, Fundamentals of Concrete. That's the prescribed book. There's the book. There's the book. Fundamentals of Concrete, third edition, edited by Gil Owens, published by Concrete Institute. Okay. So we need to know how to calculate our finest modulus. We are busy with aggregates. So aggregates need to be graded so that you can see the bulking and the grading of the aggregate. Okay. So it's just essential for you to read these notes on page 39 in aggregates. And then we go to the next page, page 41. That's where our grading analysis is. That's the table over there. That's grading analysis. So once you understand that concrete, there is following characteristics used in concrete. So there's grading, there's bulking, density, particle relative density, particle shape, surface texture, strength, shrinkage, geological type, alkali reactivity. Okay. So basically, this is the grading. We're doing grading now. Grading has to do with size of aggregate. Okay. But now, it doesn't mean that you take each piece of aggregate and measure, like take one stone and measure it. No, it's not like that. Although we speak of size, we do not measure a stone directly. Instead, we put a sample of aggregate into a standard sieve and shake the sieves and wash and record the necessary mass that is retained in each sieve. Okay, so basically, it's just some sieves that we have, and you put the soil in, and you see which diameters, which stone remain on each sieve, because stone don't have different sizes. So that's basically it is grading. It's seeing what sizes you have in your material, in your aggregate, what size of stone that you have. Okay, so that's the essence. So the standard sieves that will be used here is 4.7, 2.36, 1.8, 1.18, 0.6, 0.30, 0.15, and 0.075. But there's a cutoff point on how to measure if your aggregate is sand or is stone. So 4.75 is the cutoff point where you can measure the difference. So for large stone, it starts from 75 millimeters, 37.5, 19, 9.5, and 4.75. That's the cutoff point. And then your sand starts from 4.75 to 2.36 to 1.18. So it decreases up until 0.075 millimeters. Okay. But now we'll be dealing with a sample of sand. So we won't be going up to 75. We'll be going from 4.75 to 0.075. Okay. So in your exercise, this is what you're given, and you are told that you should work out the cumulative, the percentage of the total mass, the cumulative percentage of total mass, cumulative percentage passing through sieve. Okay. So the first thing you do when you get something like this, we need to add up the whole mass. Add up all these numbers and give us a figure at the bottom. So I've done the exercise here. So I've taken all of the mass, the numbers there, and added up and got to 417 grams. Okay, that's mass. So the first thing you do, I've done it on the side here. You need to take the first number. The first number here is 65. Okay, you need to say 65. There it is. You need to say 65 divided by your total mass, which is 417 times 100. That will give you 15.59. That is what you put in here. Okay, so basically your formula will always be what you have here, your mass divided by your total sum of mass times 100 will give you what you have in this bracket. In this case, we have 0 mass. We're going to say 0 divided by 417 times 100. That gives us 0. And then we go to the next one. 57 divided by 417 times 100. That gives us 13.67. So I'm going to send you a picture just to show the sidecast calculation. But otherwise, you do the same sequence up until you populate this column, this whole column. Okay, guys? Okay, after you do that, you need to add up this column. Let's call this column number 3. Okay, you need to add up the total and get the total of column number 3, which will be more or less 100. Okay, it will be 100. Okay, so the next thing you need to do now, you need to carry over your first reading on column 3 and carry it over to column 4. So this 15.59 automatically goes to the next column, the first one. And what you do now here, you say 15.59 plus the second column of column 3. And then you get 15.59 for that line. Take that 15.59 and add it to the following column on the row on column 3. And then you'll get 29.26. Take that and add it to the following row on column 3, get 54.68. You do that continuously until, guys, you get to the last one. Okay, that's fine. And then what you need to do now, let's call this one column 4. Okay, you need to add up column 4, but you only add up column 4 up until here. You add it up until 0.15. Okay, guys, don't go up under to 0.075. And that is just applicable to this exercise. If ever they are needing you to go less than 0.15, they will specify. But this exercise, you go up until 0.15 for our save, because otherwise that will be very fine sand if it goes. If it can go through this sieve, that is 0.15, that will be very fine sand, and it will require a lot of water. It won't have consistency, it will have segregation. So just read your notes about that. That will tell you. Okay, you add all of this up, that will give you 276.52. Okay, that is your cumulative percentage of total mass. Okay, guys, now we are also going to calculate what we call fineness modulus. Okay, the formula for that will always be the total mass, the total sum of cumulative mass divided by 100. Okay, so I've done that below here. That's 276.52 divided by 100. That gives you 2.765. Okay, that is where on our scale we'll find the fineness modulus. Okay, now over here on the pen, we added all of this, done all this equation and got to 100. This 100 you carry over. Okay, comes to this column. Now in this column, what we need to do, we need to take 100, okay, and we need to subtract each of the numbers on column 4. So this is column 5. Okay, so we're going to say 100 minus 15.59. Remember here, this one is carried over, so you don't need to calculate this one. So it's the next one. It's 100 minus 15.59. That gives you what? 84.41. I've also done a sidecast calculation for that below here. Okay, then you go to the next one. 100 minus 29.26. That gives you 70.74. Okay, and go to the next one. 100 minus 56.54.68, then you get 45.32. And you do so this on this column, you always say 100 minus that to get this, 100 minus that to get this. Okay, guys, this you will use to plot your graph. Okay, guys, there's a graph that you will need to plot. Okay, check your grading for your grading analysis. Okay, so let's go to that now. So this is the graph, guys. Okay, this is the graph. So all of the stuff that you calculated on column number 5, you are going to plot against this graph. You must have an axis. You must be able to draw up these lines and try to make it as in ratio as you can. Okay, now for instance, if you go to 0, you must have a scale from 0 to 100. So in 20s, okay, 0, 20, 40, 60, 80, 100. Then you must have your sieves here on this side, on this axis, on the x. 0.15 sieves, 0.3, 0.6, 1.18, 2.36, 4.75. Remember, we're only measuring from the sieve that is 0.15, not below, okay? So for instance, if we come here, we can see that 0.15 sieve, we got an answer of 6.71. We come here to our graph and we locate where could 6.71 be, and we do, you know how to do graphs, guys. So you go to and just put a dot on that, and you go back for the next one, 31.89 on sieve 0.3. Okay, there it is, and so on and so on and so on and so on, guys. That one is just straightforward, and you just draw straight lines to connect your dots. Okay, now these lines, these two lines over here, this is the limits that we can define a sand that it is suitable for concrete, for making concrete. So if you've got a sand that is falling out of these two lines, it means you must be adding an additive to try and neutralize, maybe to make a harsh concrete. But this one, if it falls within these two lines, then it is suitable to make concrete, guys. Remember, there's some sands that are not suitable because they've got organic matter, they've got clay, so they might compromise the curing strength of the and the durability of concrete. Okay, so that is this, guys. But read on your concrete fundamentals book. It will show you what I'm talking about. Okay, and then now let's go to the fineness modulus, guys. Okay, the fineness modulus, that's by definition. Let me read for you the definition. It's on page 42. Okay. By definition, the fineness modulus is a sum of cumulative percentage of material retained on each sieve of standard sieves. That is from 0.15 millimeter and coarser. Okay. That is divided by 100. Okay, guys. So starting